Welcome to Spring LIB.
For this question, we're considering a double-slit experiment where the central diffraction peak contains 13 interference fringes. How many fringes are contained within each secondary diffraction peak between m equals +1 and 2 in equation 2, assuming the first diffraction minimum occurs at an interference minimum d sine theta equals m lambda, where m, of course, is plus or minus 1, 2, 3, and so on at integer values. Okay, so given the central diffraction piece contains 13 interference fringes, we know that the bright interference fringes occur when d sine theta is equal to m lambda. And here, based on what we were given, d is equal to 13 over 2, because it's half of the amount times the distance between A. Okay, so, again, since there are 13 bright fringes on each one on either side of the central position, so you have to divide it by 2. Then for the diffraction, first minimum is going to occur at an angle that we can call theta 1. So we can say when m is equal to 1, we have d times the sine of the angle theta 1 is just going to be equal to lambda, right? Because m is equal to 1. And the second one it asked us to find was for m is equal to 2. So, and then this is a, not d here. This is a, the distance a. Now, how about when m is equal to 2? When m is equal to 2, we have a times the sine of the angle theta 2 is equal to 2 times lambda, because m was equal to 2. So now we can calculate the values of m for which, let's see, we'll start a new page. We have conditions. We have theta 1 is less than the arbitrary angle theta is less than theta 2. Then we're going to have, that means that the sine of the angle theta 1 is less than sine theta is less than sine theta 2. Well, we have equations that have sine theta 1, and sine theta 2 in it. So we can simply solve those equations for sine theta 1, sine theta, and sine theta 2 and plug them in. And we find that we have lambda over a is less than 2 times m times lambda divided by 13 times a is less than 2 lambda over a. Well, we can go ahead and cancel the lambdas and the a's out because there's a lambda over a in every single one of these. So what we end up with, if we do that, this simplifies down to 1 is less than 2 over 13 times m is less than 2. So now we can imagine values of m which would make this true. And again, m has to be an integer. So if m is equal to, let's just start out with 1, this isn't true because 2/13 is not greater than 1 and less than 2. Actually, it turns out the lowest value of m that is greater than 1 and less than 2 is 7. And the highest value of m that is greater than 1 and less than 2, if we plug it into this expression, is 12. So we have 7, 8, 9, 10, 11, and 12 as all the values of m that are acceptable that will satisfy this expression. So based on that information, we can answer how many fringes are contained within each secondary diffraction peak. We can say that there are 6 fringes between each secondary diffraction. Let me make sure that's how I spell it. Okay. We can go ahead and box that in as our solution to the question.